Hello, welcome to another problem session. So this is a problem from the website that we have been working. Okay, so it's a problem on Venturi meter. There is a heavy density oil and water flows over it. Let's get this figure and translate it to the properties we know. So water is incompressible, and this flow, you can say this flow here, this all water. This part is water. This part is water. So over here is kind of let's see, pressure here is say P1, and pressure here is P2. So if you look at it, so over here is going to push at P2, and this is not much height here, so you can say all of this is P1, although this height may affect, but we can ignore that, and this is P1 pushing on that side. So the way it's shown here is pressure here, this P2 must be less than P1, and this part is static fluid. So over here you know that pressure at A and B must be the same, right? In this fluid it must be the same. So pressure at A must equal to pressure at B. That just says that pressure 1 over here must equal to pressure 2 plus rho 0 GH, this height, right, should be equal to P2 plus rho 0 GH. So this is our basic observation, because static fluid, rho 0 is static. Now the second fluid rho is actually not static, it's flowing. So fluid rho is not static. So here I'm going to assume that non-viscous. I'm going to assume that, and I'm going to assume incompressible. So about this fluid flow, I'm going to assume these two. These two assumptions give us equation number 2 is the same. There's no branching, here. So it's very simple, Bernoulli. And even Bernoulli, we just have volume rate at 1, volume rate at 0.1, 0.1 being over here, or same thing over here, must be volume rate at 0.2, and this gives me one equation, which is A1 V1 equals to A2 V2. This is equation 2, and it gives me Bernoulli equation, which is this combination of P at 1, pressure, absolute pressure at 1, plus the density of kinetic energy V1 square half, and because these are same height, we can call that for potential energy for PE equal to 0, so I don't have to it's the same reference on the both sides, so I don't have to really write anything down the other side. P2 plus half rho V2 square plus potential energy this side, density at the second side is 0. Okay, so the P1 is that, and we can see that we can definitely write P1 as that. So let's write this P1 as, using that, P2 plus rho 0 GH, and you can see that this P2 cancels with this P2, and we want to know V1, so V1 is here, so this V2 we can replace by V2 is equal to V1 A1 over A2. So let's see what we have. We have rho 0 GH plus half rho V1 square equals to half rho A1 over A2 square V1 square. So we can combine this. So V1 square should be equal to rho 0 GH, and we should divide by, well, P2, and you'll have this minus that, rho A1 over A2 square minus rho. So this is the final formula that comes from simplifying this, and you can just, now we have all the this is easy to calculate outside of it here, so let's each of them calculate outside. So A1 over A2 square will just simply be pi d1 over 4 pi over 4 d2 square, so it's actually d1 over d2 to the power 4 power. So we have d1 over d2 to the power 4 power, and d1 over d2 is 5 over 1.5. So this is 5 over 1.5 to the power 4 power. We can just take the rows out from here, and so this becomes 1, and this is equal to rho 0 per row. I mean, not this row. So let's write this 2 times rho 0 is 1.8 over 1, and G is 10, and H was given to be 2, and downstairs we have 5 over 1.5 to the power 4 minus 1. So that should we should do a calculation, and so I get 0.59. So the V1 will be square root of 0.59, and everything is in centimeter, all of these guys, but the G was in meter, so we should we have a meter and H was in centimeter, so square root of meter centimeter over second square. So we should convert this square root of 59 centimeter over second, and let me get the which is 7.7 centimeter per second. So instead of this, you can see instead of this I should have used instead of this I use 1,000 centimeter per second square. And if you carry through, there was 100, factor 100, we'll factor 100 here, and that's how it becomes centimeter per second. So that's the answer. So hopefully that's correct numerical value, but I wouldn't want you to bog down on numerical value. Let's go look at the problem again. So a couple of things we have to notice. First thing, we had to notice that at this, I'm in this blue, I'm in this this liquid, which is static, and I'm at the same height, meaning I will have the same pressure at those 2 points. So that's, and then that I converted to pressure over here and pressure over here. So there's a little bit of approximation here. Pressure wherever at this point across here is. I'm assuming that pressure is same everywhere, but and it's not bad approximation, but that's another approximation I made. I said that whole pressure on this side of this blue is the same as it's coming from this side plus this liquid. And because the densities are 1.0 and 1 sufficiently different that I can maybe ignore this differences over here. And that's one approximation I made. Using that, I was able to translate this information into that information. And I need that information in the Bernoulli equation. And I need the conservation of this to actually write everything, get rid of one of the quantities. Here we got rid of V2. And the rest is just algebra, okay? In many times, instead of say if you had instead of water here, right? Say I had air. Suppose this was airflow over some tube. You'll get very similar answer. You'll get. You will still have the tube, and this is used in say airflow systems in the big buildings. They want to monitor the air. Now you say I have this. This is air. This is all air. Say if I have air. So looking at the extension of this problem. So air is flowing here and here. Could I go ahead and do that? So this will, you can see that this part will be okay, this part will be okay. Where will I run into trouble? Well, I'm assuming that this fluid rho, which is air now, if air, then this will not be incompressible. Air is a gas and it's compressible. But it turns out to a large approximation, this is still works. This is amazing, it still works, that you can use, even if it's air, even if this is air, you can say, okay, I have a problem here. It's not incompressible, but I'm going to use Bernoulli. I'm going to still use Bernoulli and this. So still you should use Bernoulli to answer questions like this, okay? Even though you are going to get an answer which is approximately, it's only in good approximation though, and it's fine, because when the air is flowing, the idea is when the air is flowing in here, this unless you have constricted it too much, it's still flowing freely and there is not much compression going on here. So since there's not, even if it's compressible, not much compression going on here, and because of that, you can, even if this got violated, even this is violated, we can still use these two fluid flow. All right, so that's it. I hope this was good. So a couple of reminders. One is to subscribe to this channel if you can. Tell your friends about this channel. And finally, like if you like this kind of answers, and you can check out physics bootcamp.org. Take care. Bye bye.